When we talk about sustainability, most of the times the first thing that we think is either clean ways of producing energy, just like wind turbines or solar panels, or new ways of using this energy, just like with electric vehicles. If you are into engineering, one thing that you might think is new ways and more efficient ways of producing our products, just like with additive manufacturing. Well, another important part of sustainability is how well we're using the energy we produce and the products that we make. And let me tell you, we are not doing a good job. Today, I'm going to talk to you about two main losses in engineering, friction and wear. Both are present everywhere. Do you want an example? Put your hands together and start rubbing them against each other. You'll start feeling the heat, right? This heat is you transferring energy from your body into motion, into heat, by rubbing two different surfaces, your hands in this case. Now, if I asked you to do that for a few minutes, maybe the whole duration of the talk, you start noticing some blistering, some dead skin on your hand. That would be wear. Well, it's kind of seem negligible, but if you go to industrial applications, then things start to be significant. What you see now is how much each country consumes of energy and how much they waste due to friction and wear. Well, it still doesn't look like much, but if we add them all together, you'd see that we're wasting more than the entire United States consumes, and we're almost reaching China. There are a lot of different ways that we can waste energy by friction and wear. Today, I'm going to talk about mainly transportation. If you think about transportation, what we have is road transportation with trucks, buses, and cars. We have airplanes, we have trains, and we have ships. Well, if you were to organize them by the number of vehicles, then road transportation would be the highest one. But another way of looking into that is in terms of energy intensity, which is a measurement of how much energy you need to transport 1 ton of cargo per 1 kilometer. Then aerospace industry comes first. So it makes sense for us to try to minimize energy and friction losses in the aerospace industry. If you focus on an airplane, more than 10% of the energy goes to overcome friction. And more than 105 billion Canadian dollars are spent in maintenance. But 40% of all that is just in engine parts. But what makes the engine such a demanding part? Well, when you think about the engine of an airplane, most likely you think of this. That huge thing attached to the wings that makes that rumbling noise that troubles you throughout the whole trip. However, when a mechanical materials engineer is thinking about an engine, he thinks about this, a cross-section of an engine. More importantly, the high temperatures and pressures that are inside there. I'm talking about more than 1800 degrees C and more than 30 atmospheres of pressure. This is really demanding conditions. So what we want is try to minimize and control friction and wear in this application. Well, the usual way to control friction and wear is either by lubrication or coatings. You can think of lubrication just like when you're doing the exercise with your hands. If you put some oil or some hand soap or something like that, it will make it easier to move, right? This means that you're losing less energy to make the movement. This would be lubrication. Coatings, on the other hand, would be like putting some gloves. Then the contact will not be between your hands, but between the gloves itself, and you would worn out the gloves and not your hands. Well, unfortunately, in such high temperatures, lubrication is not that feasible. The high temperatures will burn any oil that you try to put in, and it will lose its lubricating properties. So we have to go with coatings. But even that, there are few materials that can do that can work in such conditions. So what can we use? Well, we could use either metallic coatings or ceramic coatings. Another option, however, is to combine both of them, making a metal matrix composite or ceramic matrix composite. This way, you can combine both materials, both properties of the materials, into one single coating. But what if we added even more materials? Let's say one more metal and one more ceramic. Then what you have is a multi-component coating. This way, each different metal and each different ceramic can have a different role to protect the part that we want. A material could be used for providing lubrication at higher temperatures, solid lubrication. Meanwhile, another material can resist oxidation, or resist corrosion, or resist wear. And combining them, we can make a coating that is stable throughout a different range of temperatures. This concept was actually applied for a NASA Research Center in the form of two materials, PS304 and PS400. Both work really well for their application. What I want to do in my project is try to see if those will work well for the application that we have, and if so, how they are working so well, and try to propose new combinations that can work well for our application too. How we're going to produce this coating? Well, the technique that we use is called atmospheric plasma spray. It consists of a gun and attached to a robotic arm. This arm moves back and forth, covering the entire surface of the sample. Let's take a closer look at the gun. What you see now is a cross-section of the gun. Gas flows from left to right, either argon or helium or other inert gases. And as they flow and approach the tip of the gun, we apply a huge voltage there. This voltage can dissociate and ionize the gases and make plasma, just like Helena just told you. This ionized gas and plasma is really hot and can melt all the particles that we put in. These melted particles are accelerated towards the coating or the surface that we want to protect, building up the coating. Well, we actually did that. By using this technique, we produced a coating using data from literature for the parameters of spray or deposition. This is what we got. So what you see in the top part is the coating, and the bottom, the coated sample. Well, let's remove this box for a moment so we can see the coating. In this type of image, it's an electron microscopy image. Different contrasts have different meanings. What I mean is that different materials have different atomic weight, and then it shows different in the image. A white contrast means a heavier element, and a darker contrast means a lighter element. Based on that, we can see that we have the metal 1, which is the bright one, the metal 2, which is the gray one, and we have those small particles that are the ceramic 1. However, we noticed that we didn't find the ceramic 2 that's supposed to be there. Furthermore, the coating had really bad properties like mechanical strength, adhesion, and cohesion between the particles. The last problem that we have is that the coating is really thin, indicating a really bad deposition efficiency. So what we tried to do, and based on the lack of the second ceramic, because though that one is the one that has the highest melting point, we thought that maybe what happened is that the stream was not hot enough to melt all the particles. In order to test that theory, what we did is a set of experiments, and we increased the flow rate of helium on the spray. Well, the helium has an effect of helping the heat transfer between the particle and the stream and makes the particle heat more. Furthermore, it also increases the temperature of the stream. As we start increasing the amount of helium, we start noticing more and more coating being deposited, up to the moment that we reached the limit that we had in the equipment, and we also didn't want to burn anymore the samples. So if you heat too much, the sample might be burned. Then we did another cross-section, just like the one that you saw, another electron microscopy image to see what we got. And this is what we got. On your left is the coating that we produced at first, and on the right, the coating after the optimization parameters. Now, we can see the metal 1 that we already know, the white one, the gray one, the metal 2, the ceramic 1 is still there, and the ceramic 2 now is present. The coating also is really more thicker than what we had before, indicating that now we have good deposition parameters for producing our coatings. Okay, but now we have a suitable coating, a good coating. How do we test it? Well, ideally, what we would do is put it on the turbine or on the engine, put it to run, and then see how it goes. However, this is really not possible under the conditions that we have. So what we need to do is try to replicate those conditions in a small-scale experiment. We do that by using a tribometer, just like the one you see in the image. What you see here in the bottom part is our coated sample and the counterface on top. So if we were to draw schematics for that, this is what you'd see. The coated sample, the coating that you cannot see right now in the image because it's too thin, and the counterbody or counterface. Well, now, if you put that into motion, what you would see is that different things can happen at the surface. Material can get mixed and oxidized and form what we call a tribofilm. Material can also get detached from the surface and attached to the counterbody or counterface, forming what we call a transfer film. And material can leave the wear zone, calling what we call a wear debris. Well, why am I going through this? Because it is in this part that we will find out why the material behaves so well and what is being formed on the surface. Based on the information that we collect at this contact zone, we can propose different materials and new conditions to produce our coating and get the best result possible. We have some preliminary results that I'm going to share with you now. Well, first, we test for the friction coefficient, which is a measurement of how much energy you're losing. In this case, the lowest amount of friction coefficient, better it is for energy consumption. It means that you're losing less energy. The baseline that you see is a material well known for us that is already being applied. When we tested the PS304, what we see is higher friction, especially at the end of the number of cycles that we ran. However, the PS400 showed really good results and really promising results for our application. Now we need to check wear, right? We want friction and wear. When we did the wear test and we observed the cross-section, what we see is that the PS400 showed less wear than the other materials, almost five-fold the baseline that we had, which is really promising. What I want to do now is understand why this material is behaving so well and try with different loads, different speeds, and different temperatures to replicate the conditions faced by the engine before we can put it there to work. Today, I talked to you mainly about aerospace applications and materials to withstand high temperature. But this is not only limited for our aerospace industry. We can circle back and apply those anytime we have a high temperature, high pressure application. Furthermore, we can use it in other industries just like manufacturing. And one last note, there are some studies that show that if we correctly address the issues of friction and wear, we can save up to 18% of energy that we're losing in the short term only. That can reach up to 40% in the long term, and we can also save a lot of emissions in carbon dioxide and a lot of Canadian dollars. However, our change must start now. Thank you.